The Advanced Metalworks enterprise currently has two active projects, the first of which is Cast in Steel. Cast in Steel is a competition where teams from many different schools manufacture a weapon that gets tested for its durability and historical accuracy. This year, the weapon is a 15th century horseman's axe. Our team designed the axe so that the axe head and the langet would be casted separately and connected by pins into the wooden handle for weight reduction and historical accuracy.
So here the employees at Baycast are currently lining up the cauldron to ensure that it is meeting up with the mold and a pilot hole where they're going to pour into. And then once they are confident, they are going to tilt the cauldron to pour, where we can see the stream coming down into the mold. And then in a moment, you'll see flames spark out from the top as air holes to allow for the pour to cool off as it is being cast.
So after receiving the casting from Baycast, we had to start finishing process. So finishing, it involved cutting off the risers and gating. Used a angle grinder and a cutoff wheel to do the majority of this. Even post-cast, it was not a hard grinding process. The material was soft enough to not chew through these discs. And then once they were cut off, used the flap wheel to smooth out the surface to get ready for machining.
The wood that we selected was ash wood. We picked it because it's a very common choice for axe handles, and it's also historically accurate. It's what they would have been using in the 15th century. The shape of the axe handle is oval. This is to help the wielder index the blade within their hands and instinctively know which side the blade is facing.
For annealing, we chose to anneal because 4340 steel is notoriously hard to machine, and when we anneal, it brings down the hardness significantly, so it makes the ductility a lot better to machine with. So because of that, we ended up choosing a 1400 degree Fahrenheit heat temp for 1 hour due to the decarburizing that 4340 can face, and so putting them in bags also helps prevent decarburizing. And from there, after it was put in for an hour, we cooled off the furnace to 1,000 degrees and let the axe handles or the axe heads go down accordingly. And then after 1,000 degrees was reached, it was then air cooled.
The first step was to machine the back of the large cone riser. This allowed us to fixture the axe head so we could do the rest of the machining processes. Then we machined the cone at the top of the axe head to make the spike. And drilled the cloverleaf pattern as well as drilling the holes for the langets after machining the tang that would fit into the axe handle.
The final step after machining was to assemble the axe by inserting pins through the hole slots on the wooden handle so that the axe head would be properly connected to the wooden handle. The method of non-destructive testing for our axe that our team went with was a hardness test. In the end, we were not able to utilize the langets due to the weight requirement. The second of Advanced Metalworks Enterprise's two active projects is called the Extruded Aluminum Testing Project, which entails the extrusion, machining, mechanical testing, and data analysis of 5 aluminum alloys. The first step in this project was to get the 5 aluminum alloys into properly sized billets so that they could go through the extrusion press properly. The next step was to take the 5 aluminum billets and run them through the extrusion press so that the aluminum could be flattened out and be ready for machining. After extrusion, our team members cut roughly 20 wishbone-shaped pieces out of each of the 5 aluminum alloys. The aluminum wishbones were then taken in for mechanical testing, where our members tested each piece until failure due to tension loads being applied at a constant strain rate. The final step in the project was to analyze the data we collected from the tensile testing so that we could determine the strength characteristics of each alloy.
Alloy 5 has the highest ultimate tensile strength, while Alloy 1 has the highest ductility. The yield strength of alloys 1 and 2 are comparable, as are the yield strengths of alloys 5, 6, and 7. On average, alloys 5, 6, and 7 have higher yield strengths than alloys 1 and 2.